I was a kid, around 10 or so. So I sort of felt like I was going to grow up to build the next, the Jetson robot, which in Spanish cartoons is called Robotina. Our mission is to build embodied AI responsibly to benefit humanity in the physical world. That has been our mission for the last decade. And you can think of our North Star as solving AGI in the physical world. That's what we're after. I think the key difference here is that we're not taking the model and then specializing it just for Aloha or specializing it just for Apollo. It really is the same set of weights that works in all of them. And honestly, at the beginning, we couldn't tell if it was just generalization or if it was actually cross-embodiments. I mean, I think it's every roboticist's dream that the robot can watch a video or just watch humans around them doing things and then learn from that experience, right? We certainly do that. We learn from observing others do tasks. And it used to be before that everybody in the team was like, this will happen after my career. And now we're actually having discussions about like how far out. Are we talking 5 years? Are we talking 10 years?
We have with us Carolina Parada. She leads the robotics team at Google DeepMind, building foundational technology towards robots that can ultimately become helpful and integrated into our daily lives. Hi, Carolina. How are you doing?
Hi, thanks for having me.
So you have had a fascinating career. Can you walk us through your journey, your inspirations, and what drove you specifically to robotics?
Yeah, I mean, I've always been very excited about robotics since probably I was a kid, around 10 or so. So I sort of felt like I was going to grow up to build the next, the Jetson robot, which in Spanish cartoons is called Robotina. And so I went to school to study electrical engineering and electrical and computer engineering. And later I did my master's in control systems. And then when it was time to choose my PhD, I started looking more around like machine learning in general, and decided to actually go and work at Johns Hopkins on speech recognition. And so I took a diversion there, but I was really excited to work there and learn a lot about. That's where I learned everything I know about machine learning and then deep learning. And then I came to Google actually for the first time to work in the speech team. So I joined Google before voice was a thing for any of the Google products. The speech team was primarily a research team. And then during my time there, we worked on voice search and Google and OK Google for Google Home and Google Assistant and all of that fun stuff. And then at some point, I wanted to come back to robotics. So I did a little bit of work at NVIDIA, leading some perception teams for self-driving cars. And then finally, I came back to Google in the robotics team, which I was definitely my dream team. And I've been here ever since. So at Google, I've been leading a lot of the different research efforts. So I used to lead the navigation and whole body control and body reasoning, and then later simulation. And then eventually I started leading the entire team. So right now I lead the entire Google DeepMind robotics team. And we're super excited about, all of the research that's been happening. It's a team that has been working on foundational work for robotics for at least a decade.
The ChatGPT came out in 2022 and it shook the entire field. Were you surprised like everyone else? And what went through in your mind at the time?
Yeah, I mean, definitely it was like, I think, a pretty meaningful moment for like the AI community. I was not surprised because obviously there were a lot of efforts at Google on LLMs. So I was like, what's new? We already have this. But I think what was surprising was the engagement, the external engagement, which was really, really meaningful. And I think it was a lesson for like the entire community, how bringing this research into products, even if it's so that people can play with it and that researchers can get feedback from it, is actually really important. So that was the biggest lesson for me. But yeah, at the beginning, it took me a little bit. I was like, why are people so excited? We already had this for. So yeah.
Right. So for people who are unfamiliar, what is Google DeepMind trying to achieve in robotics, and how is it different from other Google efforts in the past?
Yeah. So, I mean, the team from the very beginning has been working on really foundational work. Our mission is to build embodied AI responsibly to benefit humanity in the physical world. That has been our mission for the last decade. And you can think of our North Star as solving AGI in the physical world. That's what we're after. And over the last 10 or plus years, we've been developing a lot of like new techniques that completely rethink the way you solve robotics, right? And there has been significant progress in the last 3 years, but it goes back a lot more. Like, just to give you an idea of some of like the things introduced by the team just in the last 3 years, we introduced LLMs and VLMs to robotics, right, as a planning tool. And that just enabled robots to now understand natural language. It enabled them to understand concepts like put all the blocks of different colors in different corners of the table, right? Something that would have been impossible before. We also introduced VLAs, so visual language action model, so a new type of foundation model that essentially enables robots to learn from web scale data and then transfer concepts into actions, enabling it to do things like, put a robot in front of a completely unseen set of objects and then ask it to do something semantically meaningful, like, find the animal or pick up the animal or something like that. And then we've also worked on introducing the concept of cross-embodiment VLAs. So with RTX and RoboCAD and that kind of work, the idea here is that you want foundation models or AI that really powers many different robot types. So we really believe in a future where there will be a really broad range of a very rich ecosystem of many different robot types. We don't believe there'll be a single one. So if we're saying that we want to solve AI in the physical world, to us, that means that it has to be smart enough to go embody into any robot and be able to move it in a meaningful way to do a meaningful task. So those are just a few examples. We've also have a really long history of working on reinforcement learning. So like a lot of the techniques that are used in locomotion for reinforcement learning, whether it is from imitation or just learning in simulation from scratch, has also been developed by this team. And we tried it on quadrupeds. And I don't know if you remember the little soccer guys that were playing soccer with each other. That's all reinforcement learning. We've tried it in ping pong, just about any of the tasks that we had in the team. And then last year, we decided to focus on dexterity. We felt that it was one of those frontiers that needed also a bit of a revolution, and to see if we were able to do something exciting there. And so we started showing, for example, really powerful policies that could do things like laundry and tie shoelaces and do in-hand manipulation. So a lot of work in that area. And so just basically what we've done this year is bring a lot of those breakthroughs and combine them with powerful multimodal foundation models like Gemini in order to like really take another big step forward with Gemini Robotics, which is essentially our most powerful visual language action model that brings all of Gemini's multimodal understanding to the physical world by essentially adding actions as a new modality in Gemini. So the idea is that most robots really struggle when you put them in a new situation, right? You change their environment, you change the objects, you change the way you ask it to do a task, and it completely breaks down. And if it actually is thinking with Gemini Robotics, then it can use Gemini's multimodal world understanding to tackle a new situation because it knows, right, all of these concepts from Gemini. So that's roughly what our trajectory has been in the last few years. And we continue to work towards improving it. And there's still a lot of work to do.
That's great. So Gemini Robotics, the first version came out in March. And more recently, you released the version 1.5. So for the latest version, what are the key underlying upgrades and how does that translate into results?
Yeah. I mean, importantly, I think for Gemini Robotics program in general, we really care about developing models that are really general. So you want to always be evaluating how robots are able to tackle new situations. So anything out of distribution, different environments, different objects, different tasks, etc. So generalization continues to be an area we want to improve. Interactivity is another area we really care about. So making sure that humans can interact with the robot and change its behavior, and that you can also change the environment and the robot understands that. And then the last piece is that we want to make sure that while we're building all this intelligence, we want to make sure that the robot can handle really dexterous behavior. So generalization, interactivity, and dexterity continue to be basically key pillars that we want to improve. So that's also true in the Gemini Robotics 1.5. The biggest difference is that in 1.5, we're basically powering a new era. We're bringing physical agents into the picture. And what do we mean by this? We mean that these models are able to perceive with a lot more detail than before. They can think multiple steps ahead as opposed to just one instruction at a time. They can use tools like if you give them access to any API or web tools like search or maps, they can use that in order to solve problems. And then they can use all of this to solve more complex multi-step tasks. So the simplest way to think about it is you're going from a robot that executes a single instruction to a robot that can understand a longer problem solve, and take multiple steps in order to do it. So we've put a few examples of that when to try to convey that. It's a little bit more complex, but the idea was like if you can ask the robot, for example, to sort your trash, and based on your location, there's different rules. It can look up what the rules are based on your location. It can understand the scene in front of it, and it can basically map that into a sequence of steps in order to complete a task. And that's just one example where you had to use tools,
Right.
you have to plan, etc.
Right. Yeah, there was one really cool demo that two robot arms are packing a suitcase, and you have a new core capability, which is the robot's able to think before it acts. So this part of the capability is now on the VLA side, not just on the
Let me
planning
try to
side.
explain. It is definitely more nuanced. So first of all, with Gemini Robotics 1.5, we have three things. We have a new reasoning model, which is more powerful than before. It has more special understanding. It can also do tool orchestration. This is just Gemini Robotics ER 1.5.
Right.
We also have a VLA, which is an upgraded VLA, Gemini Robotics 1.5. And this one, it has a few capabilities, which I'll go into. And then we also have an agentic framework that can combine the two. So in some of the examples, we were showcasing the entire system. So the packing, the putting away your trash was the entire system. But it is true that in the VLA itself, we now have made some improvements. So key improvements that we have there is that we now are able to think while acting. What that means is that essentially the VLA is predicting both actions and also like thinking tokens, and that enables it to reason while it's taking actions at a different level. It also, what we found is that it enables it to operate much longer. So I could have a VLA with thinking that operates easily 15 minutes. I actually haven't left it running for a really, really long time to see how far it will go, but easily 15 minutes is no problem. So you could give it a task that requires multiple steps. Obviously, once it's done, it's done. But if you keep changing the environment, it will continue thinking and taking action until it feels it's done, until it can observe and predict that it actually completed the task. So yeah, it's primarily there's one model which can now think and act. And then if we combine this one model with also the reasoning model and the agentic framework, then you can see how it starts getting in a much capable of completing much more complex tasks.
Right. And you mentioned that the orchestrator part, the embodied reasoning model, is able to look up on the web for information like weather or local recycling rules. So how did it learn to identify the gaps in the contextual, environment, and then go on to look up on the web for that information?
Yeah, I mean, it's very, very similar to how it works with agents outside robotics. It's essentially a reasoning model that can orchestrate tools. So the way that it learns to plan a sequence of steps in order to complete a task, which is a reasoning task, it can also say, oh, as part of this planning, I don't have this information and I should look up if I have any tools that will help me solve this problem. So you do have to explicitly prompt it to say, these are the tools available to you, but it's an orchestrator at the end of the day. And an orchestrator plans a sequence of steps, and that sequence of steps is now made available tools like web tools. So it goes beyond search. Like a developer can decide to give it, I don't know, an API for your inventory system, and they can look up if something is in your inventory, for example. So it's simply that's just as simple as it goes in terms of how it works.
Okay. And how is the data, the robotics data for the models gathered? Is it teleoperations? Are there other modalities like simulation that's being used?
Yeah. Yeah, I mean, obviously, foundation models are what we're doing here is we're teaching a foundation model how to operate in the physical world. So certainly, we add robotics data to help teach it and inform it of what it means to pick up an apple in the physical world. So we include definitely teleoperation data from different robots. One of the things we always try to do is make sure that our models are not getting specialized for any one robot. So we make sure that we gather from different robots. And we certainly have efforts around simulation and around even, leveraging other data sources. But I will say today, the strongest data source is still teleoperation, and simulation is the second strongest. And we use these tools not only for data generation, but also for like fast evaluation. You can imagine like running evaluations on real robots is very time consuming. So we leverage quite a lot of simulation for evaluating policies before running it on real robot. And at the end of the day, we only feel satisfied if the performance on real robot is consistently doing what is expected.
And so the two main components, how are they trained differently from each other? What's the main difference in the training set? And do they have to have some common intelligence so that they are on the same page when interacting?
Yeah, that's a great question. I think they're fundamentally, so they come from the same, they are Gemini models. So they're just simply Gemini models that have been um, specialized for reasoning and actions. That's basically all they are. So we don't do anything special for them to orchestrate with each other. You can think of the VLA as another tool that the orchestrator can call. And if the VLA is capable of, for example, executing a sequence over 15 minutes, honestly, the other model just simply uh, checks in and tracks progress, but doesn't need to have any more detailed um, understanding of or alignment with what's happening on the VLA. And it, so yeah, no special alignment between them. They both leverage data from data that goes beyond robotics and data from robotics. So yeah.
Right. Are these two models eventually going to converge, or are there fundamental benefits of having them like a separate components?
Yeah, I mean, we certainly ask all these questions all the time. I mean, one of the things that we do in our team is make sure that we're questioning every assumption that we have pretty much every time we
Right.
plan. So absolutely, there is people that are excited about, can we just have a single model? And there is folks excited about having the separation. I will say that from my experience, understanding what the needs are out there, talking to folks in the industry, I think there is quite a bit of interest on having a reasoning model that is really, really, really good for robotics. And so there's lots of applications where you have your existing skills, and what you want to do is just bring the intelligence as a layer that works with your existing skills and with your existing control systems that you have in place. And that brings a lot of value. So I think regardless, the reasoning model is an interesting one. And so I think, yeah, we believe that we should continue to invest on it.
Okay. Another major core upgrade was the cross-embodiment transfer, where a task is trained on one robot but can run on another robot without having to have extra data for the second robot. So was that an emergent property of the training set, or did you have to make some clever tweaks to the architecture?
Yeah. I mean, we've always, like I said before, we've always been after like solving intelligence in the physical world. So to us, that really means that the model needs to be able to understand its embodiment and adapt on the fly, ideally, to any new robot. So we've always been going after that goal. And I think I would say the surprising thing in this release was like we were simply expecting that we would get stronger and stronger cross embodiment transfer, but still require some degree of adaptation on the new models. And once we started training the models without any kind of like specialized post training for the robot, we realized it just works. And obviously, that is the best case that you can have. We still need multiple embodiment data in order for it to just transfer. But I think the key difference here is that we're not taking the model and then specializing it just for Aloha or specializing it just for Apollo. It really is the same set of weights that works in all of them. Um, and honestly, at the beginning, we couldn't tell if it was just generalization or if it was actually cross embodiment. So we created some benchmarks where like we only put certain types of motions and objects in one and certain types of motions and objects in the other one. So it's not enough that it's objects, because if it's just objects, it could just be object generalization, right? We started also putting different motions. Like in this case, I'm only going to be able to touch things that are in front of you. In this other case, only going to be able to do things on tabletop, for example. And that's when we started really believing that there was transfer. So I think there's still a lot of work to be done. I think obviously for these robots to be incredibly valuable in society, they need to be operated at much higher accuracy rates and lower latency and all of that. But it was just super exciting for the team because certainly was, let's just put it this way, it wasn't like we didn't believe it was a goal that we could achieve in this release. Always a goal for the team, but very excited that we got farther than we expected. And yeah, we'll continue to do a lot of research in that area because it's incredibly valuable. As you know, any time you spend on any one robot is expensive, right? It's time that you're investing on that robot with the humans and the physical space. So if you can have some robots that just learn from other robots' experience, you're immediately augmenting the opportunity for the type of tasks that robot can do. So
Right. So does
yeah.
this cross-embodiment transfer also pave the way for learning from directly from humans, maybe where humans are wearing some wearable headgear and walking around, navigating the world, doing things, and you capture all that data and useful patterns in that data for the
Yeah,
robots.
I mean, I think it's every roboticist's dream that the robot can watch, a video or just watch humans around them doing things and then learn from that experience, right? We certainly do that. We learn from observing others do tasks. Um, I believe you will still always, as humans do as well, need a little bit of practice time for you to really get a physical sense of what it means to do a task, probably depending on the difficulty of the task. But yeah, our dream is that you can learn without robots in the loop, for sure. I don't think that we're there yet. I think there's significant research to be done to get there. But every step that we take where we get more cross-embodiment transfer just brings us closer to that world. Because what we're observing that the model is doing is that it understands better what it means to do a motion and what impact it should expect in the world from doing that motion. And that applies to a human or a humanoid or a robot with a gripper that is trying to do a motion, right? Like, for example, if you're opening drawers like this or like this, is understanding what it means to do that motion is something that transfers beyond robots. So, yeah, that gets us very excited, but we still have significant efforts on getting to that level where we can actually learn from humans effectively.
Right. And the generalization happens on different levels, on different axes. Like you need to be able to add new tasks for a completely new environment with a minimum amount of data. And also you want existing tasks to become more robust to maybe visual variations or instructions or object types. So how do you make sure, what are the maybe the challenges you're facing so that to make sure all the axes are progressing simultaneously without major trade-offs?
Yeah, I mean, I think definitely some of the biggest challenges we face now is how do you really broadly evaluate these models, right? If you're saying that you're claiming that this model is a general, then, technically to prove that you have to test it in a huge amount of situations. And so we're leaning also, again, we have research on like how do we lean on evaluating 99.9% of our policies without running it on robot. But at the end of the day, we still run our policies on robot in order to like really feel confident of our results. So there is a challenge on like, yeah, distribution of objects, distribution of scenes, distribution of motions. One of the biggest gains that we observed in this release was generalization across motions, and primarily is because we're just learning across different better from the data that we have. I think that's the best way to put it. We can and better across different robots. But yeah, I think with physical robots, the challenge is usually how do you get like physical evidence that this is general. Um, I will say in all of our benchmarks, what we do today is that we have benchmarks for generalization across different axes. And the minute the generalization gets strong enough, we update the benchmark to make it much harder. So, and that means we have to give up on evaluating. Maybe before we would do, I don't know, thousands of iterations on evaluating scene or background generalization. And now we do much less so that we can spend more time on new ones. So it's a bit of a trade-off, but our hope is that once these models are basically just evaluated daily across robots that are not even the robots in our labs, then we can track over a much broader set of applications how much are they really generalizing.
On a recent Dwarkesh podcast, Richard Sutton, he pushed back on the idea that imitation can be a good prior for reinforcement learning. So, how did you feel about that in the context of robotics? And do you see imitation learning at scale with complemented by reinforcement learning is a good pathway to achieving truly general purpose robotics AI?
Yeah, I mean, absolutely. We are super excited about. We have a long history of working on reinforcement learning, and that has not gone away. Even as we have quite a bit of emphasis um, on our Gemini efforts and our imitation learning research and all of that. So we believe the best will actually be achieved with a combination of both. And indeed, I think that a big boost that imitation learning is bringing when you're combining it with reinforcement learning is that it's giving you some like very strong biases about what things are reasonable to do. And in the case of robotics, that's important, right? Because reinforcement learning does, like if you start from scratch, we'll do a whole lot of exploration, which will put the robot all over the map and then take a lot longer to learn, not to mention that it will just have a lot of wear and tear on the robot. The robot itself, the joints will just like degrade a lot faster because if you have no priors, that's what you're doing. You're fully exploring the entire space. So yeah, the believer that the combination would be a big win for the entire community. I'm sure many people in the community are looking at that. Um, and yeah, there's active research on that beyond just our traditional research on reinforcement learning for whole body control, which is also an active area in the team.
And Google DeepMind is also working on world models, Genie 3 being the latest one. It's a video generation model that's action controllable. So is the Gemini Robotics team going to tap into those world models where robotics agents are, wandering around and learning about the open virtual worlds?
So yeah, the short answer is like one of the biggest, strongest, I think, benefits that we have towards like really truly solving AI in the physical world is the deep engagement that we have with the different teams in Gemini, in Genie, in Veo. We work very deeply together, and in many of them, we actually have a portion of our team is part of that team in order to help us advance the technology in core Gemini, for example, to better understand the physical world, our team is part of those efforts. And some of that actually goes in regular Gemini releases. So that's just one example. And similarly, we collaborate with Vio and Genie. We already have, I think, some efforts where we're using basically these models, Vio Genie, to like evaluate our models and be able to test, put the robots in new scenarios that they never seen and evaluate how they would do in those scenarios. We didn't talk that much about it during the release because there was a lot of information packed there, but that's absolutely something that we're leveraging today. And there's significant other research that's happening in the team about how to leverage it better. So yeah, absolutely, that's one of the areas of research in the team.
What type of applications are developers using Gemini Robotics 1.5 for? And what can you share about any real-world deployments or testing that's happening?
Yeah, so we're basically, as you know, we're being very focused on just improving the capabilities of these models, and it's definitely, I would call it early days for general purpose robotics. So at the moment, the way we're bringing and engaging with the external world to bring these models is through different efforts. So we have, for example, some partnerships like the Aptronic partnership. We also have a trusted tester program where we are able to engage with different companies across the industry that want to test some of our models. And then we recently, actually, as part of this release, we also exposed the Gemini Robotics ER model in AI Studio so that it can be really just tested by anyone who wants to see where the models are. So the idea for each one of these ways of bringing our models out is that we want to really engage with the community externally to see how they play with our models. The AI Studio release is super recent, so we're now starting to understand how folks are using it and the gaps. And really, what we're doing here is just learning as much as possible about what the areas that we want to improve and understand how we're doing especially when these models are being used outside our labs. And so in terms of applications, I think just looking at some of the trusted tester programs that we have, there's a really broad diversity. Our trusted tester program, first of all, is again just a tester program where folks are able to play with the models and understand how they're doing. And there's a really broad range. I mean, there's folks working on more logistics applications. There's folks playing with them for more assembly tasks. There is folks working on it for like human robot interaction and just reasoning and planning. And the agentic systems are only put out just recently, so I haven't like really understood how folks are finding it. But that's one of the areas that we want to dive into to see how this is useful and whether there's a lot of interest in the community. So I think it's very, very early days, but we're super excited to see how the community starts using them. And we engage with folks on the Trusted Tester program to understand that better.
And there's a humanoid robotics boom going on right now. There is a lot of hype. There are maybe 50 companies designing their humanoid robots. And you said you want to be an robot agnostic platform. Does humanoid form deserve like a special focus as kind of a predominant form in human-centric applications?
Yeah, so I mean, obviously, yeah, very aware of all the exciting things happening on the humanoid space. I think it's really, really cool for the community to be pushing on this frontier. We definitely believe the world will be diverse. In the robotics world will be diverse. There will be many different robot types, and we want to make sure that the intelligence that we're building is capable of adapting to any of these type of embodiments. Having said that, I do think that it is important that we have a real understanding of how our AI can basically help humanoids become really intelligent and really capable. We find them fascinating. There's two aspects. Obviously, what you hear most often from the humanoid companies is, well, these robots can have a human form factor. That means they can go in any human spaces, which is completely true. And also just from as an AI researcher is incredibly exciting because it's one of the most complete representations of what AGI would feel like in the physical world, right? The best example that we have of AGI is a human brain. So a human body or embodiment that looks like a human is certainly very attractive in an area that we always want to invest in. So I certainly think it's an important form factor. We still always want to make sure that it's not the only one. So, yeah.
And when do you think we will have Gemini Robotics AI running on robots in homes, doing day-to-day chores? And what are from purely from technological point of view, what are the key limiting factors to achieving that?
Yeah, I mean, I know there's a lot of talk about bringing humanoids into home. My take on that is that the home would probably be just the hardest environment to go into, and uh, certainly I think that we will get there. And it used to be before that everybody in the team was like, this will happen after my career. And now we're actually having discussions about like how far out. Are we talking 5 years? Are we talking 10 years? And part of the reason for that, I think, goes beyond the capabilities of the model. I think that we can make significant progress just judging by the rate of progress in the last 3 years. You can't easily imagine within 5 years having a really, really strong model that can understand the world really well. I think the challenges will go beyond that, though. There's aspects of safety and privacy and social adoption and human robot interaction and um, basically policy. There's all kinds of different aspects that I think will come into play in the humanoid space. We at the moment simply see the home as one of many environments that we want to be able to operate in. And so we just see it as another benchmark that is relevant and that we should be working on. So it's not like we're waiting 5 years to start working on it. We certainly think about home tasks constantly and have benchmarks that are representative of it. But I believe for factors even beyond AI capabilities and hardware capabilities, that it will be one of the last frontiers. But I believe at the same time that there's a lot of value, a lot of learnings that we can have by bringing these robots into human-centric spaces way before the home. So
Okay.
I think there will be many opportunities for bringing value.
You've done some work in self-driving as well, and Waymo published a scaling study this year where they showed that the models predictably improve with scaling the compute budgets. So are those scaling laws analogous in robotics as well, or robotics is a completely different beast because of high dimensionality and all the chaos?
Yeah, I mean, I think what I can say is we certainly leverage scaling laws to accelerate our own understanding of what we should be um, spending our own compute on, right? There's lots of opportunities to be, as you've seen from even this discussion, there's just lots of research threads going on at all times. And simply if we work more efficiently by testing things at smaller scale before testing them on the best models. I think with robotics, one of the key things though is that there is going to be meaningful constraints into how big you can go in terms of these models, right? Because the latency constraints are so critical for the proper function of the end-to-end system. So I think you're gonna get some benefits from it, but it's not gonna be to the same level as, for example, just regular LLMs or VLMs that have zero latency constraints.
So the robotics seem to have become about data and deep neural nets these days. Is there a value in learning, or somebody maybe who is starting right now, is there a value in learning the classical physics-based approaches and theories? Would that help in building an intuition for building the latest techniques in AI?
Right. I would definitely recommend that the people are building a very, very strong foundation and also tracking where also the more end-to-end neural network based models are going. I think it is important to have both. One of the things that we're super proud of is that our team is actually incredibly diverse in terms of the backgrounds that come into the team. We have quite a bit of folks with physics simulation background and control background and what we call hardcore roboticists, right? We have hardware engineers, and we have folks that come from completely different fields in different parts of AI, and folks that have worked in products at Google. So I think that diversity really enriches this culture of we should be constantly reevaluating our assumptions, and we should be constantly having meaningful discussions about what aspects of all of our knowledge can come together to build a new solution. So very respectful of bringing all of those perspectives together. We certainly have folks that do traditional robotics or with a traditional robotics background that contribute to all of our solutions. So yeah, I believe that it is very valuable, and you still also need to be able to work on end-to-end learning approaches. So I think that is important.
AI and robotics is promising an abundant society. There are a lot of positives for it, but there is also a lot of anxiety around loss of purpose, loss of jobs. So how do you think we should navigate these ethical issues and this large scale disruption that's going to be caused by physical world AGI?
Yeah, I think that, well, first of all, we are super committed to building AI solutions, and this goes beyond robotics, that benefit society as a whole. That's just part of what GDM's mission and principles are. So we're always looking for opportunities where the benefits outweigh the risks, and where we're overall creating a really positive impact in society. I think it's pretty early days, and it's hard to fully understand how this will evolve the use of robotics in everyday spaces and in also manufacturing, in logistics, in all of these areas. So it's hard for me to predict, but we do work, as with the rest of GDM, on any AI models, with a responsibility team that sort of studies the impact of AI in society, and robotics is no exception. So we just treat it as one other application of AI that we evaluate, and we work very closely with those teams so that they track what are the opportunities ahead based on the technology, and then we understand the impact that can have, and that help us guide um, our strategy and how we want to bring this out. So pretty early days, but the best way to think about it is the same way GDM is looking to responsibly bring AI to society. Robotics is no exception.
To wrap it up, what would be the top reason you would personally have a humanoid robot at your home?
I joke all the time that the real reason that I got into this field is that I didn't want to do chores. So definitely, I'll be super happy to let a robot do my dishes, my laundry, and pick up around the house. No problem. So really excited to get there. I think many of us are very inspired by that. Um, and yeah, I hope hopefully it will be even broader than that, right? You can do pretty much any task that you set the robot to do and is physically capable of doing.
I'm very excited for what you're building. Do you have any final thoughts?
No, but thank you so much for taking the time. I am super excited about the future of robotics, and we really hope that that we continue to engage with you guys and with the rest of the community to understand how the models are doing and bring that back. And yeah, our mission is to build the most helpful robots. So super excited to connect with the rest of the community to get there.
Thank you so much for your time, Carolina.
Thank you so much, Sven. Bye.
Bye.